All right, we're back. We're still on page 2 of notes 15. We're talking about these summation formulas and trying to like get in the practice or back in the practice or whatever, see them maybe for the first time of utilizing them. So we've already done 3 problems. Let's take a look at this next one. See if we can kind of like, we're gonna do this 2 ways. We're gonna, well, maybe. We're gonna look at it, we're gonna see if we can do it with our summations and then maybe peel it apart, see if it like relates to our function type stuff somehow. So I think it does by initially looking at it. So for whatever reason, there's just a 3 over n hanging out, and that's okay. 1 to n. All right, so we've got 2 and then minus 5, so that's like minus 3. And then we have 2 times this, so we have 6i over n, so plus 6i over n. So that's when we simplify. So now I'm going to take the step where I like divide this up, break this up a little bit. I'm actually going to make it, so equals negative 9 over n from 1 to n. 1 to n, interesting. It's not a number up there. So I took the negative 3 out. I'm dealing with like this right now. So that's just the sum of 1. And now I'm going to take, so what can I take out? I is changing, so I can't factor an I out, but I can factor anything else out. So I can actually factor a 6 over n out. So I'm going to have 3 over n times 6 over n, and then the sum of I. So 3 times 6 is 18, and then n times n is n squared, and then from 1 to n of I. So that's where we are at this point. I find this encouraging. And I will tell you why in a second when we simplify this a little. So this will be negative 9 over n. And then if I do the sum of 1 from 1 to n, that's just n times 1. So that's just n. So that comes from here. And then 18 over n squared. The sum of I from 1 to n, well, that's actually literally the formula, right? It's n plus 1 over 2. Okay, so here's the reason, let me highlight. The reason I find this encouraging, and this is just from doing a million of these. When you're doing these, if there are these weird n's hanging around, these tend to work out a certain way. The way they tend to work out is that this n here should cancel with whatever n's are given here in the numerator. So n's in the denominator of a coefficient should cancel with n's in the numerator of whatever formula you use. So here, like this n and this n are going to cancel. So I'm thinking I'm on the right track. And then here, this is going to ultimately give me an n squared, right? Because it's n times n plus 1. That's like n squared plus n. But n squared, that's the highest degree in the numerator. And the denominator here has n squared. So you're pretty much on the right track when that happens. So here I'm going to go with negative 9 plus 18 n, and oh, actually I guess we could just make it 9. Okay. I'm not good at erasing. Like I over erase. n plus 1 over n squared. Now, it's not a part of the problem, but I could take the limit as n approaches infinity of this thing. Like that would not be an issue for me. So I'm going to do it in a different color because it's not really related, but, well, I mean, it's very related. If I let n go to infinity, negative 9, n plus 1 over n squared. This is actually just going to be negative 9 because the limit of negative, there's no n there, so that's just negative 9. This is like n squared. It's like 9n squared plus some garbage over n squared. If n goes to infinity, that's just 9. So this, that gives me 0. Now, what could that mean? And is that right? I don't really know if that's right or not. Let's take a look. Let's try to dissect this. So I look at this thing, and I'm going to say, I think that inside of here is a function with something plugged into it. I think the thing being plugged in is this. Because if I say that this is x sub I, right? Let's say that. Then the function, then what's in there is 2 times x sub I minus 5, or just 2x minus 5 with something plugged into it. So I'm going to say that my function f of x is 2x minus 5. And I'm going to say the thing that's being plugged into it, x sub I, is 1 plus 3i over n. Now 3 over n showed up a different place also. It showed up here. That's not bad either. And the reason that that's not bad is that I think what that is, I think that this part, 3 over n and 3 over n, I think that's actually delta x. I think that delta x is 3 over n. And I think our summation looks like this. F of x sub I delta x. So I think what we're really dealing with here is a right Riemann sum for this function, but then where? So here's a thing that we're going to do a lot. And if you took analysis, you might remember this. First, find x0, then find xn. So x0, if I let I equal 0, this goes to 0, you just get 1. If I let I equal n, you get 3n over n is 3 plus 1 is 4. I think what we're doing is, how am I going to do this? 1 and then 4. Okay, so axis 1 and then 4. Okay, so bear with me a little. So I need to go to 4, 2, 3, 1. All right, when I plug in 1, I get -3. Like this. When I plug in 4, I get 8 minus 5, I get +3. So let me draw this. So I think what I just found is this area, which if you look at it, if I draw it perfectly, it makes a little more sense. It makes sense to me that that area is, the total accumulated areas would be 0 because you're getting this negative region and then this positive region just cancels it out. I think that what we found when we took this limit is actually the integral from 1 to 4 of 2x minus, what is it? 2x minus 5 dx. I think that's what we found. And I think that makes sense, right? So you write Riemann sums to approximate definite integrals. Maybe we can go from Riemann sums back to the definite integral. I think we definitely can. Let's see if we can do it on the next one. So I see a lot of the things that make sense for that. I see a 1 over n, and then here there's this is 1 over n times I. It's like I times delta x. I think we can do it. So first we're supposed to do this using the summation formulas. So let's do that. And then we'll see if we can work it out another way. Ooh, not I, that's I. 1 to n. All right, ooh, gosh. All right, so 16, square it, multiply them together, times 2, 8i over n, squared, I squared over n squared, and then plus 3. Okay, so I'm gonna rearrange it a little bit. 1 over n, because you definitely don't want to do like extra steps on these if you can avoid it. So it's gonna be 19, and then we just have 8i over n plus I squared over n squared. So I will break this up again because I think that it's probably useful to do that. I'm gonna make it 19 over n, the sum from 1 to n of 1, plus 8 over n squared, the sum from 1 to n of I, and then 1 over n cubed, which is kind of weird, except it's I squared, and I squared is n plus 1, 2n plus 1. That's like n cubed in the numerator, so I'm okay with that. Sum I squared. Whew. All right, so what do we have? This is 19 over n times n, plus 8 over n squared, and then n plus 1 over 2. 1 over, that's not an n at all. N cubed, and then it's n plus 1, 2n plus 1. That 2 there, by the way, killer when you take a limit. All right, so it's not gonna get better than this. Well, I mean, it can look a little, like a very, very tiny bit better. What if we just took the limit of this? I'm gonna say that this whole thing, I'll say is like a of n. And if I took the limit as n approaches infinity of a of n. All right, so this is definitely just 19. Here we have like 8n squared and some garbage over 2n squared. So 8 over 2 is 4. Here we have 2n cubed plus a lot of garbage over 6n cubed. 2 over 6 is 1/3. So I think, what is this? 23, 69, 70, I think 70 over 3. If I took the limit. Problem doesn't tell you to take the limit. So why would I do that? Well, I'm now going to try to peel this apart and make a Riemann sum out of it. I'm going to try to figure out the definite integral this could represent. And the way I do that is I go hunting for a function. And it's a tip off a little bit that you can see this. This is related to your like x of I. So looking inside here, find a function that something is plugged into. I'm going to say this function that something is plugged into. I think this is what's being plugged in. I think the function is just x squared plus 3 with something plugged in. So I'm going to write that down. I think that f of x is x squared plus 3. And I think the thing being plugged in is 4 plus I over n. And so I think that delta x is 1 over n. And then what I want to do is I'm going to find x0, and I'm going to find xn. So x0 is 4 plus 0 over n, so 4. Xn is 4 plus n over n, so 4 plus 1 is 5. So I think that this thing we just found is the integral from 4 to 5 of x squared plus 3 dx. So what I'm going to do on my calculator is I'm going to find that integral and see if it's 70 over 3. So let's switch to a calculator and see what it says. So if I do the integral of x squared plus 3, x is the variable going from 4 to 5, I get 70 over 3. Woo! If I do 1 over n, let's see what happens here. I'm going to punch in the original, right? 1 over n, the sum from I equals 1 to n of quantity 4 plus I over n squared plus 3, and then just press enter. Okay, like great. But what I really want to do is take the limit. So limit as n approaches infinity of the answer, I get 70 over 3. So it actually is working. This is like some very high level stuff. And let me go back to the notes and show you what you're required to be able to do at the end of this page. So everything we've done is nice, but what you're required to be able to do by the end of this page is definitely this stuff, right? So like get this, get these, go from these to these, and then do arithmetic. So here, start with this, make sure you can do this, make sure you can simplify this, be able to break it up into these, and then apply the formulas to get here. And then maybe do arithmetic, maybe you can leave it like that, who knows, depends on directions. Be able to expand, and then if you want to, you can skip a step and go straight from this, to applying the formulas. That's totally fine. You could have done that here. You could have gone from here to here if you wanted to. You could have gone from here to here. You actually, you could have gone from here to here. Oh, you could not have, hold on. You go from here to here. That would be fine. Down here, starting with this, be able to get to this. And then it's nice if you can take the limit, for sure. Like you should be able to take that limit. So that's good if you can. After taking the limit, it's all just bonus at this point if you could dissect it and come up with this. Similarly here, make sure this can be turned into this, simplified here, use your formulas to get here. So you need to be able to get here. It's a bonus if you take the limit and get this. It's even more of a bonus if you can look at this and figure out this corresponds to this. So that's what you need to be able to do is what I said you should be able to do. All the other stuff's just bonus stuff. So don't be too intimidated by it, but just know that very soon, it'll be kind of second nature for you to do that. And that's really why we do it. So I'm going to cut the video here. I will be back in the next video to do some more. So I will see you there.